Welcome back to the energy conversion lectures. In previous two lectures, we have discussed and covered the concentrated armature windings. In this lecture, we will cover the distributed armature windings of synchronous machines. Note that almost all AC machines in practice are built with distributed armature windings and not concentrated windings. As mentioned before, the distributed armature windings can be defined as the windings where the coil's sides of any phase winding are distributed in several number of slots instead of concentrated in one slot. Let's give more details. These two figures show two synchronous machines. The first machine represents two poles single-phase synchronous machine with salient pole rotor and concentrated armature windings. The second machine represents two poles single-phase synchronous machine with salient pole rotor and distributed armature windings. Let's flatten these two machines and see the differences between these two machines. In case of the concentrated armature winding machine, the machine is implemented with three concentrated coils connected in series. As we can see, in case of the concentrated armature windings machine, each side of the three coils of phase A are installed in one slot. Note that each coil of the three coils of phase A is implemented with only one turn in this example. Now, in case of the distributed winding machine, the machine is implemented with three distributed coils connected in series. As we can see, in case of the distributed windings machine, each side of the three coils of phase A are installed and distributed in three slots instead of one slot. Note that each coil of the three coils of phase A is implemented with only one turn in this example. We mentioned in previous lectures that in the practical synchronous machines, the induced voltage of the armature windings need to be large and appropriate value. So if we use the concentrated winding, a very large number of turns or coils are needed in each phase to achieve high induced voltage ER. Simply, it is impossible to put all the coil sides into this single slot. Therefore, it is not practical to accommodate all these turns or coils of the phase in one slot of the concentrated stator core. Therefore, the distributed windings are used because the distributed windings use many slots to accommodate many coils or turns for each phase and therefore able to build machine that can withstand high induced armature voltage. Basically, this explanation represents the main and first reason of using the distributed windings in practical application, and we can put it under the category of induced voltage capability. It is clear now that the distributed windings have better construction for producing higher voltage comparing with the concentrated windings machine. The other reason of using distributed winding is related to the quality of the distributed magnetic field waveform and the back EMF-induced voltage waveform. We will give more details about this point later in the upcoming lectures. Now let's recall the terms that we learned during the concentrated armature windings lecture and apply them to the distributed armature windings. Let's start with the slots per pole term. The slots per pole can be calculated by dividing the total number of slots, denoted by capital S, over the number of poles, denoted by capital P. This figure shows two poles three-phase synchronous machine with distributed stator windings, which consist of 18 slots. So in this machine, the total number of slots is equal to 18 and the number of poles is 2 poles. Therefore, the slots per pole is equal to 9 slots. We can also understand or visualize the slots per pole term by dividing the machine depends on the number of poles. Since this machine has 2 poles, we can divide it into 2 sides, one facing the North Pole called North Pole side, and the other side facing the South Pole called South Pole side. As we can see, the number of slots in each side of the poles are 9 slots. 9 slots in the North Pole side and 9 slots in the South Pole side. So the slots per pole represents the total number of slots of the stator located at one side of the rotor poles. Therefore, the slots per pole of this machine is equal to 9 slots. Let's take another example. This machine represents 4 poles, 3-phase synchronous machine with salient pole rotor and distributed windings. So if we follow the rule of identifying the slots per pole, then first divide the machine into 4 sides depending on the number of poles, then count how many slots in each side of the poles. As we can see, the number of slots in each side are 9 slots. Therefore, the slots per pole of this machine is equal to 9 slots. In summary, the slots per pole can be defined as the number of slots that are facing one pole side. Mathematically, we can calculate the slots per pole by dividing the number of slots by the number of poles of the machine. That means this machine's slots per pole is equal to 9 slots. Now let's calculate the slots per pole per phase of this distributed armature winding machine. Since this machine represents 2 poles, 3-phase machine and consists of 18 slots, the slots per pole per phase, represented by M, will be equal to 3 slots. Basically, if we focus on the upper side, which facing the North Pole, we can see that the upper side consists of 9 slots belong to 3 phases, 3 slots belong to phase A, 3 slots belong to phase C, and 3 slots belong to phase B. Now, if we divide this upper north side per phase into 3 parts, we can notice that each of these 3 parts has 3 slots belong to each phase. These 3 slots represents the term M. This figure shows 3-phase 4-pole synchronous machine with salient pole rotor and distributed windings. Based on the rules we learned, the slots per pole per phase M of this machine is also equal to 3 slots. As mentioned in previous lectures, the slot angle represents the angle between two adjacent slots and can be denoted by the electrical angle beta and equal to 180 degree divided by slots per pole. In this example, beta is equal to 20 degree electrical. Also, in this example, the slot's angle beta is equal to 20 degree as well. Now, assume we have this 2-pole 3-phase synchronous machine with salient pole rotor and distributed windings. This machine can be represented by this flattened machine. The distance between the center of two adjacent poles is called pole pitch and can be measured by either the electrical angle between the center of the two adjacent poles or by the number of slots between the center of the two adjacent poles. Note that the angle between the center of the two adjacent poles is called the pole pitch angle. The pole pitch angle is always equal to 180 degree electrical. The number of slots between the center of the two adjacent poles in this example is equal to 6 slots. Now, since the slots per pole of this machine is equal to 6, then in general we can say that the pole pitch is equal to slots per pole when it is represented by the number of slots. Now pay attention to the coil sides A1, A1' of phase A as an example. The distance between the two sides of any coil is called coil span and can be measured by electrical angle or the number of slots between the sides of the coil. Note that the angle between the two sides of the coil is called the coil span angle. If the coil span is equal to the pole pitch, then we call the coil full pitched coil. In other words, the full pitched coil is the coil where the angle between the two sides of the coil is equal to 180 degree electrical. Also, we can say that the full pitched coil is the coil where the number of slots between the two sides of the coil is equal to the slots per pole. Note that if the coil span is less than the pole pitch, we call the coil short-pitched coil. It should be noted here that the short-pitched coil is usually used in practical machines, and we will discuss it in the upcoming lecture. Now assume we have this 3-phase 2-pole synchronous machine with 12 slots stator. If we focus on phase A of this machine, we can notice easily that these two coil sides of phase A, A1 and A2, are placed in two adjacent slots as shown. Basically, these two coil sides of phase A, A1 and A2, which surrounded by these two lines, are called phase belt. These slot sides of phase A, A1 and A2 can also be called phase group or phase spread or phase band. As we can see in this 2-poles machine, there are 6 phase belts. In general, the phase belt can be defined as the group of slots of one side of certain phase winding. The phase build can either be represented by number of slots or by electrical angle. If the phase build is represented by number of slots, then the phase build will equal to slots per pole per phase M. In this example, M is equal to 2 slots. If the phase build is represented by electrical angle, then the phase build can be denoted by sigma and will equal to M multiplied by beta, where beta is the slot's angle. In this example, the phase build angle sigma is equal to 60° electrical. It should be noted here that the phase build angle sigma of the practical three-phase machines is usually equal to 60° electrical. Now pay attention to this point. The stator of the three-phase synchronous machines, or the three-phase AC machines in general, can be built either with single layer windings or with double layers windings. In medium and large power machines, the machines are usually built with double layers windings, while small machines with less than 10 kilowatt ratings are built with single layer windings. In general, the single layer means the slots of the stator have single or one layer of coils, while the double layers windings, the slots of the stator have two or double layers of coils. To get better idea about the single layer and double layers stator windings, let's take the following example. Assume we have a three-phase, 2-pole, 12-slot synchronous machine with full-pitched distributed windings. This figure shows the single-layer windings implementation of this machine. This figure shows the single-layer implementation when we flattened the machine. Based on the given information of this machine, the slots per pole of this machine will be equal to 6 slots. The slots per pole per phase represented by M will be equal to 2 slots. Note that the phase built slots are equal to M and equal to 2 slots. The slot's angle beta of this machine is equal to 30° electrical. The phase built angle is equal to sigma and equal to 60°. Since the windings are full-pitched windings, the coil span angle of any coil of the windings is equal to pole pitch angle and equal to 180°. Also, since the windings are full-pitched windings, the coil span slots are equal to slots per pole and equal to 6 slots. Half slots from this side plus half slots from this side plus these 5 slots. Phase A winding can be plotted in more details as shown. As we can see, since the machine is full-pitched windings machine, each coil of the distributed windings will have coil span equal to 180° electrical. Another indication of full-pitched coils is that the coil span slots of any coil is equal to slots per pole and equal to 6 slots. Now let's implement same machine using double layers windings. This figure shows the implementation of the 3-phase 2-pole 12 slots machine using double layers stator windings. This figure shows the double layers implementation after flattening the machine. One observation is that the slots of the phase belt of this example contains coils from the same phase because the windings of this example are full-pitched double layers winding. In other words, these two slots contain only phase A coils and does not include coils from other phases. We will see in the upcoming lectures that the slots of the phase belt of double layer short pitched coils will contain mix of coils from other phases with phase A coils. Note that each coil span angle is equal to pole pitch angle and equal to 180 degree because the coils are full pitched coils in this example. This figure shows how phase A coils are implemented in this example. It is very clear that phase A is implemented with two sets of distributed coils, light blue distributed coils and dark blue distributed coils. The light blue coils are installed in the upper slots in this side and installed in the lower slots in the other side. However, the dark blue coils are installed in the lower slots in this side and installed in the upper slots in the other side. Note that these light blue coils and dark blue coils of phase A are connected in series. In other words, the light blue coils and dark blue coils are all belong to phase A, and all the coils of phase A are distributed coils and connected in series. As mentioned earlier, the double layers windings have more coils comparing with the single layer windings. Therefore, we can produce more voltage with less number of slots comparing with the single layer machine. It is worth mentioning here that in practice, the double layers windings are more easier to manufacture because they have fewer slots for a given number of coils. Before ending this lecture, we would like to explain one more point. This figure shows 3-phase 2-pole machine with concentrated windings stator. This figure shows 3-phase 2-pole machine with distributed winding stator. Obviously, the distributed windings machine have more slots comparing with the concentrated windings machine. Although the distributed windings offer advantage over the concentrated windings, the existence of these high number of slots of the distributed windings will impact the rotor magnetic field distribution and introduce a special type of oscillation or ripple or harmonic components in the rotor magnetic field distribution. This type of harmonics is called the slots harmonics or tooth harmonics. Note that the slots harmonics can also be appeared in the rotor induced back EMF voltage if we do not eliminate these harmonics from the rotor magnetic fields. Now let's give some idea about the slots harmonics. This figure shows flattened 3-phase synchronous machine with 2-pole salient rotor and 12 slots distributed windings stator. Now, if we ignore the impact of the slots, the rotor magnetic field can be plotted as shown. However, if we consider the slot's impact, the magnetic field will be as shown. As we can see, the magnetic field introduced some oscillation because of the slot's impact. Basically, the oscillation or the ripple in the rotor magnetic field is introduced because the air gap between the stator and rotor changes because of the slots. As we can see, the air gaps between the stator and rotor alternate between small air gap and large air gap. These changes of the air gaps affect the reluctance of the magnetic field between the stator and rotor and therefore cause oscillation or ripple in the magnetic field distribution. So when the air gap is small, the reluctance is small and therefore the magnetic field is high. However, when the air gap is large, the reluctance is large and therefore the magnetic field is low. It should be noted here that the slot's harmonics frequency depends on the number of the slots of the stator. That means the slot's harmonics order or frequency will be high if the stator has high number of slots. It is worth to mention here that the slot's harmonics cause several issues into AC machines. Basically, the slot's harmonics of the magnetic field introduce harmonics in the generated AC voltage of the AC generator. Also, the slot's harmonics produce unwanted torque components that can cause vibration and noise into the machine. In conclusion, the slot's harmonics are unwanted harmonics and need to be removed by some methods. We will talk more about the slot's harmonics in the future lectures. Let's conclude this lecture at this point and we will continue in the next lecture. Let me know if you have any question. Also, make sure to subscribe to this channel so you do not miss any lecture. Thanks for listening. I am Ihsan Al-Nabi and it was a pleasure sharing this lecture with you. Thank you.